The Moon, our only satellite. Barren and void of oxygen and life. Where temperatures on its surface range from a blistering 230 degrees Fahrenheit to a frozen minus 290 degrees at night. Here, there is no weather, no wind. It is serene, still, unchanged for millions of years. Beyond it, the Earth. Surrounded by a thin gaseous layer, its surface often remains hidden beneath the ever-changing veil of clouds. This layer of gases protects the Earth from harmful solar radiation, limits the temperature extremes, and contains the weather that scars and molds the features of its surface. On Earth, there is never such a thing as no weather, and the rate at which our atmospheric conditions change can be dramatic. As pilots, we must become attuned to the atmosphere and the weather it contains. Since the air is our medium of movement, understanding weather phenomena and the forces behind them are important considerations. The atmosphere that surrounds the Earth is relatively thin. Although it extends several 100,000 feet into space, about half of the total atmosphere is compressed below 3.5 miles. Many people have the false impression that the atmosphere is mostly comprised of oxygen, but in reality, only 21% of the total gas is oxygen. Nitrogen makes up most of our atmosphere, with carbon dioxide, argon, and other gases making up the remaining 1%. The atmosphere is made up of several basic layers, with the lowest layer being the troposphere. This layer slopes upward from about 20,000 feet at the poles to about 60,000 feet at the equator. Most of the weather which you will be concerned with will be found within this layer. Above the troposphere is a thin layer known as the tropopause, which acts as a lid on the troposphere, keeping most of the moisture within the layer below. The stratosphere extends to about 22 miles above the surface. The air within this layer is very dry and stable. Few cloud formations penetrate into this layer. Above the stratosphere are the mesosphere and the thermosphere. These layers have very little effect on the weather. The gases in the atmosphere contain molecules that are constantly in motion. As the air is heated, these molecules speed up, creating more space between them. The result is fewer molecules per given volume of air. When the air is cooled, the molecules become less active, meaning more can exist in a given volume of air. This cooler air is heavier and denser than the warmer air. The differences in air density are the basis for the movement and circulation of the atmosphere. To demonstrate this principle, suppose we have two rooms, one which contains cold, dense air, while the other has warmer, lighter air. When the door is opened, the air begins to mix. The heavier, colder air slides under the warmer air, creating a cold draft on the floor. As the cold air fills the bottom of the room, the warmer air replaces the colder air. On a larger scale, the draft created between the rooms is called wind. Air replacement due to these density changes drives our major weather systems. This density difference is due to the pattern of global heating. At the equator, light from the sun strikes the surface at an almost perpendicular angle. Near the poles, the surface of the Earth is largely turned sideways to the sun. This results in more atmosphere between the sun and the Earth at the poles. This greater amount of atmosphere cuts down the intensity of the sun's rays. Also, the same amount of light that would cover a given area on the equator is distributed over a far larger area at the poles. The result is less heating energy per square mile. As the sun's radiation heats the tropical areas of the Earth, the air becomes less dense and rises. Because less dense air does not exert as much pressure, a permanent low-pressure area forms near the equator. Nearing the top of the troposphere, the warm air is displaced sideways, away from the equator. The air continues northward and southward, slowly becoming cooler until it begins to descend near the poles. This colder descending air creates a permanent high-pressure area near the poles. The air then returns along the surface, back toward the equatorial areas, to replace the rising air. If the Earth didn't rotate, there would be a continuous circulation pattern from the polar highs to the equatorial low. But because it does, this theoretical one-cell circulation pattern becomes a three-cell pattern. In this circulation pattern, the air near the equator still rises and flows toward the pole. But this branch, known as the Hadley cell, only reaches about 30 degrees north. Here it combines with sinking air from the Ferrel cell that corresponds with a semi-permanent subtropical high-pressure area. Near 60 degrees north, the warm surface winds of the Ferrel cell and the cold winds of the polar cell collide, rising to produce an area of low pressure. In addition, these airflow patterns are affected by Coriolis force. In order to better explain how Coriolis works, let's use the example of two ball players attempting to play catch on a merry-go-round. As the pitcher throws the ball, it travels in a straight line, but not to the catcher. To the thrower's perspective, some force seems to be turning the ball to the right. This same situation applies to air as it flows from the North Pole to the equator. Because of the Earth's rotation, the wind seems to be deflected to the right. This apparent rotation is called Coriolis force. Atmospheric pressure, or the concentration of air molecules over a given area, is measured in terms of inches of mercury, or millibars. 1 inch of mercury is equivalent to approximately 34 millibars. The measurement of pressure is done with the use of a barometer. This instrument is nothing more than a partial vacuum within a glass tube containing mercury. As the pressure of the air exerts a force on the container of mercury, the mercury will rise. The average atmospheric pressure of the Earth will make the mercury rise 1,013.2 millibars, or 29.92 inches. This measurement is considered to be standard pressure. During periods of higher atmospheric pressure, the force exerted upon the mercury is greater, which forces the mercury to rise. The reverse happens during periods of lower than standard pressure. If we imagine standard air pressure as a plane, we can visualize the relationship between air masses with different densities. On the left is a high-pressure system, or a mass of denser than standard air. It is more dense at the center of the mass. On the right is a low-pressure system, or a mass of less dense air. Pressure changes occur more rapidly directly between the center of the high and the center of the low. As we rotate the image to a top view, we can draw lines around the areas that appear to have the same height, or in this case, the same amount of atmospheric pressure. These lines are called isobars, and they are drawn on weather maps to represent areas of equal pressure. By using these lines, you can determine the position of high and low pressure areas. You can also tell how large or severe they are by the number of lines and how they are placed. Notice how the isobars are closest together directly between the high and the low. The closer the lines, the stronger the pressure gradient. Air from a high-pressure area will flow directly toward a low with a force which relates to the pressure gradient. If the Earth didn't rotate, highs and lows would exchange wind directly in this manner. However, Coriolis force from the rotation of the Earth is also acting on these systems. As winds spill off a high-pressure area in the northern hemisphere, they are deflected to the right. This results in a clockwise flow around a high and a counterclockwise flow around a low. As the wind is driven around these systems, the air closest to the surface is slowed by the friction of the ground. When this happens, the Coriolis force is diminished until the pressure gradient force becomes greater. The resulting wind tends to flow across the isobars toward areas of lower pressure. At altitude where airflow is not affected by the surface friction, the wind continues to flow parallel to the isobars. In addition to creating large patterns of wind around highs and lows, differences in atmospheric density can cause wind flow on a local level as well. In areas near the ocean or other large bodies of water, local changes in heating and atmospheric density can cause daily wind flow patterns. During the day, water slowly absorbs heat. On the nearby land, the sun's radiation only penetrates a few inches into the soil. The land surface heats up much quicker than the water. As the air over the land warms up and begins to rise, air over the water is being cooled down because of the cooler surface of the ocean. The cool air then flows inland to replace the rising warm air. This produces a sea breeze flowing inland from the ocean. During the night, the land cools very quickly. The air above the landmass begins to cool and sink. The ocean, now warmer than the land, begins to warm the air above it, causing the air to rise. The flow of the cycle now reverses, and in the evening, a land breeze will be experienced. Local wind patterns can also form as the result of mountainous terrain. One of these is a foehn wind, which occurs when there is a mass of cold, dense air near the top of a mountain range. As the air pushes over the top of the range, the cold air begins to descend down the other side. As this air accelerates and replaces the warmer air beneath it, it begins to compress and warm up. As the air heats, it will eventually become warmer than the air it is replacing. This causes the atmosphere at the bottom of the hill to become warmer. These winds can become very strong, with gusts exceeding 120 miles per hour. In the Rocky Mountains, they are called Chinooks. In the Sierra Nevada mountains, they are the Santa Ana winds. Regardless of their names, these winds can produce large amounts of damage and are hazardous to aircraft, both in the air and on the ground. They can occur during what would normally be perfectly good VFR weather, and is one of the reasons surface wind reports are important to you when receiving a weather briefing. We have seen how heating and the differences in air density can produce wind. The other major force in the formation of weather is moisture. Moisture occurs on our planet as a solid, a liquid, and a gas. Within these states, it can take many forms. We see moisture as clouds, as rain, hail, or as snow, ice, or water. Dew and frost are also forms of moisture. How water changes back and forth from state to state is very important to the formation of weather. We have all experienced the effects of evaporation, such as water evaporating from a lake. When water turns from a liquid to a vapor, the process requires heat. This heat energy is drawn from any available nearby source and is stored by the vapor. When the water vapor is returned to a liquid through the process of condensation, the latent heat that was stored during evaporation is now released. The heat exchange during evaporation and condensation is a major factor in the vertical movement of air columns. Thunderstorms, for example, can be developed by this force. Originally, the air begins to rise through a force such as the sun heating the surface, which in turn warms the air above it. As this warm air cools and eventually condenses, the latent heat released from condensation will, under the right conditions, continue or increase the strength of the updraft. If this process continues, a thunderstorm can develop. In vapor form, molecules of water exist between other molecules contained in the atmosphere. When the air is warm, more room exists between the molecules of air. Therefore, more water molecules can squeeze between the air molecules. When the air is colder and the air molecules are closer together, less water vapor can fit between the already close air molecules. For this reason, cold air cannot hold as much water as warmer air. Dew point is the temperature at which an air mass becomes completely saturated with water vapor. In other words, it will hold as much water as the temperature will allow. When an air mass becomes completely saturated, condensation occurs. Let's say that we have an air mass with a temperature of 55 degrees Fahrenheit. If the dew point is also 55 degrees, then the air is 100% saturated. If condensation nuclei are present, then condensation will occur. Clouds, fog, and dew are all forms of condensation. When water that is formed on the condensation nuclei becomes too heavy for the atmosphere to support, then precipitation occurs. Since the moisture content in an air mass is relatively constant, the air mass must usually undergo some form of cooling in order for condensation to occur. For example, if the air is 50% saturated at 55 degrees, then the air must be cooled to about 37 degrees in order for condensation to occur. When the temperature reaches 37 degrees, this air mass will be 100% saturated. Weather is something that we must deal with daily as pilots. It is constantly changing and infinitely complex. Knowing the basic driving and manipulating forces of our Earth's weather patterns will help you to understand the more detailed conditions and concepts that will be introduced in the following weather sections. Being able to understand the concepts of weather development will not only help you understand the current conditions, but will also help you anticipate future changes as well.
It looks like it's going to be a cold one today. An Arctic cold front moved into our area around 3 this morning and has already dropped 3 to 4 inches in some parts of the city. The air mass associated with this front is stable, and with all the moisture that's being pushed up from the Gulf, we're in for snow the rest of the day and possibly tomorrow.
Every day, all over the world, people are dealing with the effects of the weather. In the previous section, we saw how the forces of air density, Coriolis, temperature, and moisture worked independently of each other. In this section, you'll see how they interact to produce the weather phenomena we see every day. The type of weather we experience is, in part, related to whether or not air rises or falls in relation to the surrounding air. The term used to measure how much relative resistance an air mass has to this vertical movement is called stability. A stable air mass, for example, resists vertical motion. This inhibits large cloud formation, heavy precipitation, and severe weather. An unstable air mass, on the other hand, has the potential for significant cloud development, turbulence, and hazardous weather. The weather in the tropics is a good example of unstable air. With its warm temperatures and high humidity, daily thunderstorms are commonplace. Air mass stability plays a large role in the development of weather. We can best see this role in the development of clouds. There are 2 basic types of clouds, cumulus and stratus. Cumulus clouds are formed by rising currents of air, which gives them a piled up or bunched appearance. They warn of unstable air, turbulence, and showery precipitation. Visibility outside the precipitation is usually good. In air masses with a high amount of stability, stratus clouds may form. Resisting vertical movement, these clouds form in smooth layers and often extend over large distances. Since the air is stable, flight near stratus clouds is normally smooth. Precipitation from these clouds can be continuous and last for several hours or even days at a time. The visibility associated with stratus clouds is usually poor. In addition, clouds can further be grouped into high clouds, middle clouds, low clouds, and clouds with extensive vertical development. Cirrostratus, cirrocumulus, and cirrus clouds are examples of high clouds. They are composed almost entirely of ice crystals and seldom pose hazards to pilots. Most names of middle clouds contain the prefix alto, such as altostratus or altocumulus. These clouds are composed of water, ice crystals, or supercooled water, which is water that has been cooled below its freezing point but is still in a liquid state. They can contain moderate turbulence and potentially severe icing. A cloud with a name containing the prefix nimbo or the suffix nimbus contains a large quantity of moisture. A nimbostratus cloud, for example, can produce widespread areas of snow or rain. While classified as a middle cloud, the nimbostratus cloud can merge into the clouds formed at low altitudes. A cloud which can be very deceptive to pilots is the lenticular cloud. This lens-shaped cloud may form over mountain crests during high wind conditions. Even though it looks smooth and serene, it is, in reality, a good indication of heavy turbulence and should be avoided. The low clouds form near the surface and extend to around 6,500 feet. Clouds within this group include the stratus, stratocumulus, and fair-weather cumulus clouds. The thunderstorm, or cumulonimbus cloud, is an example of a cloud with extensive vertical development. This type of cloud can have its base as low as 1,000 feet and extend up to the heights associated with high clouds. Flight near a thunderstorm can be extremely dangerous. These hazards will be discussed in the next section. So far, we have talked about the stability of an air mass and the types of clouds which can form if the air mass is stable or unstable. But how and where do these air masses begin, and what happens to them as they move? As we discussed earlier, the global circulation patterns form high and low pressure areas. The high pressure areas, located at the poles and in the tropical areas, act as source regions for air masses. If an air mass forms over water, it is further classified as maritime. This type of air mass will usually contain more moisture than a continental air mass, which forms over the land. As an air mass leaves its source region, it is modified. The amount of modification depends on the speed of the air mass, the nature of the region over which it is traveling, and the difference in temperature between the air mass and the region. As an air mass moves, it comes in contact with other air masses of different properties. Since air masses with different temperatures and pressures do not mix very well, their boundary forms a front. As you fly across a front, you may experience discontinuities, which are rapid changes in atmospheric conditions. These include temperature, wind, and pressure. Temperature is probably the most easily noticed change, but the two which should concern you more are wind and pressure. An undetected change in the wind could cause you to drift off course inadvertently. When flying through a front, you should expect a wind shift and adjust your navigation accordingly. Since there is usually a pressure change when you cross a front, you should reset your altimeter to the correct setting to avoid being higher or lower than the indicated altitude. Fronts are defined by the type of air mass that is in the overtaking position. In other words, if a colder air mass is overtaking a warmer one, then the resulting front is called a cold front. This definition is relative, though, because a cold front can be any temperature, as long as it is cooler than the air mass it is overtaking. As a cold front moves, it replaces warmer air at the surface. Since colder air is denser, it pushes the warmer air aloft. If this warmer air is relatively dry and stable, stratiform clouds form in the vicinity of the advancing cold front. If the warmer air is relatively moist and unstable, cumuliform clouds may form along the front. A rapidly moving cold front can create thunderstorms many miles ahead of the frontal boundary. A line of these thunderstorms parallel to the front is called a squall line and can contain violent weather. The thunderstorms in a squall line can grow to 65,000 feet and can be especially violent. These storms often produce heavy rain, large hail, and even tornadoes. In contrast to a fast-moving front, the slope of a slow-moving cold front is not as steep and the lifting action is not as great. Therefore, the weather is less severe. When a warmer air mass overtakes a colder one, a warm front exists. Because of the difference in relative densities, the warm air will slowly slide over the colder air. This can result in very little vertical air movement. If enough moisture is present and the colder air mass is relatively stable, stratiform clouds usually form. These clouds may extend for many miles ahead of the front. However, there may be some cumulus clouds present in the form of embedded thunderstorms if unstable air is present. The weather associated with a warm front usually includes low ceilings, fog, and a subsequent reduction in visibility. When two air masses of relatively equal strength collide, a stationary front may form. Here, there is very little movement. The weather associated with this front can vary depending upon the temperature, moisture content, and stability of the air masses. It is usually a mixture of that found with both warm and cold fronts. One of the most complicated frontal systems is the occluded front. In this case, a fast-moving cold front is overtaking a slower-moving warm front. There are two types of occluded fronts. The one shown here is a warm front occlusion because the air ahead of the warm front is colder than the overtaking cool air mass. Of the two types of occlusions, this one produces the more severe weather. The other type is a cold front occlusion. Here, the cold air is replacing cool air at the surface. This type of occlusion generally doesn't produce weather as poor as a warm front occlusion. However, like the warm front occlusion, the weather associated with it is hard to predict and can produce a wide variety of weather considered dangerous to most general aviation aircraft. With weather patterns constantly changing, it is important to understand the factors behind their development and to get a good pre-flight weather briefing before flying. In the next section, we'll take a look at how these weather systems can be hazardous to flying and what you can do to predict these conditions and avoid them. Weather hazards come in many forms. Some are clearly visible, while others may be encountered unexpectedly. In this section, we'll look at some of the common hazards and discuss how you can avoid them. The thunderstorm is a weather phenomena which is capable of producing very violent conditions. Thunderstorms can develop rapidly, and the hazards associated with them can exist for several miles beyond the storm itself. Three atmospheric conditions are necessary for their formation. The first is unstable air, which allows for extensive vertical development. Second, there must be some type of lifting force, such as convection. Finally, moisture must be present. A thunderstorm passes through three stages: cumulus, mature, and dissipating. The cumulus stage is characterized by updrafts, which may extend from near the Earth's surface to several thousand feet above the visible cloud. Also, during this stage, water droplets form into raindrops. However, instead of falling to the Earth as precipitation, they are suspended in the cloud by the updrafts. The second, or mature stage, begins as the raindrops begin to fall to Earth. You can expect the most violent weather to occur during this phase. At this time, the raindrops have grown so large that the updrafts can no longer support them. As they fall, they pull air with them, creating downdrafts, which may exceed 2,500 feet per minute. As the downdrafts reach the surface, they spread out, creating strong, gusty surface winds. The dissipating stage begins when the cell becomes predominantly downdrafts. During this stage, the intensity of the precipitation decreases. It is also during this stage that the upper-level winds often blow the top of the cloud downwind, giving it an anvil appearance. However, this does not necessarily mean that the storm is over. Severe weather could continue well after the anvil forms. While thunderstorms usually have similar physical features, they can differ in intensity, degree of development, and associated weather. Lightning is one of the weather hazards that always accompanies thunderstorms. Other hazards might include heavy rain, hail, turbulence and gusty surface winds, and even tornadoes. As you gain experience, you'll learn how weather limits your flying. But regardless of your experience, you should always avoid intentionally flying into or near thunderstorms. To do this, you must know where they exist or are likely to develop. You can determine this by checking weather reports and forecasts prior to departure and during your flight. If widespread thunderstorms are being reported, you might find it necessary to delay or cancel your flight. If you encounter thunderstorms while airborne, you should never attempt to fly over them. These clouds can build faster than your airplane is capable of climbing. Flying below the cloud can be just as hazardous because of the extreme turbulence produced by the downdrafts. And you shouldn't try to fly around a thunderstorm unless you can maintain at least 20 miles between it and yourself. If that isn't possible, it might become necessary to turn around or fly to an alternate and wait for the storm to pass. The turbulence associated with thunderstorms varies in intensity from light, annoying bumps to severe jolts that can damage your airplane and injure its occupants. To minimize its effect, slow to maneuvering speed or less. One form of turbulence, called wind shear, is a sudden shift in wind speed or direction. It can occur at any altitude and in a vertical or horizontal plane. Wind shear is often associated with a more serious phenomenon called microburst. A microburst is an intense, localized downdraft which descends from the base of a convective cloud. As the air reaches the surface, it spreads out in all directions, often forming in a circular motion. This circulation creates an area of severe horizontal and vertical wind shear. A wind shear is particularly dangerous when it's in the proximity of an airport. To show you what can happen, suppose you're taking off into a microburst. You would initially experience a headwind and an increase in performance. When the aircraft reaches the point where the wind shears to a tailwind, it experiences a severe decrease in performance, which could lead to disastrous results. Some airports are equipped with a low-leveled wind shear alert system, which allows controllers to advise you of significant wind differences on the field. Whether or not this system is available, any time a thunderstorm is in the vicinity, you should anticipate the presence of a microburst. While most microbursts are associated with heavy precipitation, moisture does not have to be present. They sometimes occur in virga, or streamers of precipitation that trail behind clouds and evaporate before reaching the ground. If there is no precipitation, a ring of dust on the ground, or trees being blown in different directions may be your only indications. Do not take off or land at an airport when you suspect a microburst exists. If you are in the air, delay your landing or divert to another airport. Most microbursts will pass over an area within a few minutes. Another form of turbulence occurs near mountains. It develops when the air is stable and winds in excess of 40 knots are flowing horizontally over mountain ridges. However, some turbulence may develop when the winds blowing over the ridges exceed 25 knots. If the air is unstable, the air on the windward side of the ridge will probably be extremely turbulent. If there is enough moisture present, cumulus clouds and possibly thunderstorms may develop. As the wind crosses the ridge, it spills down the leeward side. This may create violent downdrafts which could exceed the climb capability of your aircraft. If the air is stable, the wind flow will be smooth on the windward side. As it crosses the mountain, it tends to flow in layers or waves. The crests of these waves are often marked by lens-shaped clouds. These clouds are called standing lenticulars because they form in the updrafts and dissipate in the downdrafts, giving them an appearance of remaining stationary. Anytime this type of cloud is present, you should expect turbulent conditions. If you fly at airports used by large aircraft, you should be alert for another type of turbulence called wake turbulence. This type of turbulence occurs when a large airplane is generating lift and is most pronounced at low airspeeds and high angles of attack, such as when taking off or landing. Although it eventually dissipates, wake turbulence can persist for several minutes. If you encounter it as you're attempting to take off or land, the results could be disastrous. At controlled airports, controllers are required to provide minimum separation between small and large aircraft. However, you have the responsibility for avoiding wake turbulence. To ensure that you don't encounter wake turbulence while landing behind a large departing aircraft, you should touch down well before the airplane's rotation point. When making an approach behind a large aircraft that has just landed, stay above its glide path and touch down beyond its touchdown point. When departing behind a large aircraft that has just taken off, you should lift off before the airplane's rotation point and remain above its flight path. If a light crosswind is present, you should fly upwind of the large aircraft's flight path. And finally, if you're departing after a large aircraft has landed, make sure you lift off at a point beyond the touchdown point. Another weather hazard you should be familiar with is structural icing. Since it occurs only in visible moisture when the aircraft's surface is at or below freezing, you're unlikely to encounter structural icing until you're instrument rated. The major reason icing is dangerous is because it changes the shape of the airfoil and destroys its lift. It can also increase the weight of the airplane and restrict control movements. Frost is a related element that you are more likely to encounter as a VFR pilot. Like icing, it can be hazardous because it interferes with the smooth airflow over the wings, resulting in a loss of lift. You should never take off unless you have removed all frost and other ice formation. As a VFR pilot, virtually all of your flying will be done with reference to the ground. When your visibility is restricted by elements such as haze, smog, smoke, fog, blowing dust, snow, or volcanic smoke and ash, you may have problems determining your position. Fog is one of the most persistent weather hazards and is frequently the cause of surface visibilities being less than 3 miles. It can form rapidly, changing from VFR to IFR conditions in just a few minutes. Anytime you have high humidity, a small temperature dew point spread, and light surface winds, you should anticipate fog and have an alternate course of action if it does occur. Although volcanic eruptions are not a common occurrence, volcanic smoke and ash can pose an extreme flight hazard. In addition to reducing flight visibility, volcanic ash can cause compressor stalls and flameouts in jet engines. In piston-powered aircraft, it can also cause severe damage or engine failure. Ash clouds are most dangerous close to the volcano when an eruption has just occurred. This is due to the large amount of ash particles, hot gases, and dust. Because volcanic ash is highly abrasive, control surfaces can be damaged and the pitot-static system and ventilation systems may become clogged. When volcanic material is injected into a stable atmosphere, the ash and smoke may be carried long distances by atmospheric winds. The gases and smaller particles spread out and may be very difficult to distinguish from an ordinary water or ice cloud. Currently, the National Weather Service monitors volcanic eruptions through pilot reports, radar, and satellite observations. Then, by using computer forecast models, the NWS forecasts ash cloud movements and provides subsequent advisories as required. If you observe a volcanic eruption, notify ATC. However, do not jeopardize flight safety to make a report. Immediately take evasive action by turning upwind to avoid entering the ash cloud. Don't attempt to fly through or climb above the cloud. When you are safely away and you can make your report to ATC, provide the location and altitude of the cloud, wind direction, and a description of the ash cloud and eruption. As you gain experience, you'll learn to recognize hazardous weather conditions. In addition, you'll learn that with proper pre-flight planning, you can avoid areas of potentially dangerous weather before you encounter it in the air. In the next volume, we'll discuss the types of information which are available to you and how to interpret them.
Many people believe predicting the future is a hazy, inexact process. For them, an accurate prediction depends on blind luck or good fortune. However, relying on luck to predict the weather for your flight is not wise. As a pilot, you must rely on good forecasts. Fortunately, a number of methods with varying accuracies have been developed to help you anticipate weather conditions. Have you left your house in the morning for work, noticed the nice weather, and determined it would still be nice later in the day? If so, you have made a persistence forecast. By assuming the existing weather conditions won't change during the day, you predict the weather in the afternoon will be as nice as it was in the morning. However, this method of forecasting is not reliable over long periods of time, usually not more than 1 or 2 hours. Trend forecasting predicts that, without interruption, a weather event, like a storm cell, will continue moving in the same direction and at the same speed it's currently moving. In this case, the storm will reach the airport in less than 2 hours if atmospheric conditions don't act to change its course and speed. Similar to persistence forecasts, trend forecasting is generally accurate for only a few hours. At times, predictions are based on the average historical weather for an area. Known as climatological forecasts, they are reliable in areas and times which enjoy little change in day-to-day conditions. For instance, San Francisco has a generally moderate climate and may receive less than 1 rainy day per month during the summer. The analog forecast also uses historical data for predictions. This method is useful in predicting the temperature for a given day. By combining past data for a certain day with prevailing weather conditions, a meteorologist can accurately predict the expected high or low temperature. One of the better ways to predict the weather is the meteorological forecast. A good meteorologist can reliably forecast out to 12 hours by using his knowledge of atmospheric processes. This type of forecast can be a valuable tool for pilots. Powerful computers and mathematical equations have increased forecast accuracy by modeling weather trends. The result is a numerical weather prediction. The computer runs one forecast model on top of another to determine their effects over time. Doing so produces a relatively accurate picture of future weather events. Regardless of the forecast you receive, you can be sure the information contained was collected and compiled with the help of numerous agencies. With thousands of land and sea-based reporting stations, large volumes of weather data can be collected and analyzed. Through the coordinated action of several agencies, including the World Meteorological Organization, National Weather Service, and numerous private organizations, weather information is disseminated for your use. Although the weather collection and dissemination network is extensive and thorough, it's not perfect. While forecasting accuracy continues to improve, long-term forecasts and short-term predictions of localized weather phenomena are still difficult to develop with reliability. Even though forecasters aren't always precise, the experience and skill they can provide you is superior to other methods of predicting the future. After all, when it comes to aviation weather, having the edge provided by a good forecast is better than taking your chances.
A weather check is not only an important part of your pre-flight planning, but is required for any flight not in the vicinity of an airport. A wide variety of weather reports and forecasts are available for pilots to use. Today, there are several ways you can access these reports and forecasts, including a personal visit to any flight service station, computer-based weather briefings, and weather reports by fax. Since the systems allow direct access to printed weather information, learning to decode actual reports and forecasts is just as important as ever. During this program, you'll become familiar with aviation routine weather reports, pilot weather reports, radar reports, terminal aerodrome forecasts or TAF, area forecasts, airmets, SIGMETs, convective SIGMETs, winds and temperatures aloft forecasts, and finally, notices to airmen or NOTAMs. Let's begin our discussion with a look at METAR, or Aviation Routine Weather Reports, which contain the latest reported hourly weather observations for various locations. The information for each reporting station is printed in a coded format beginning with the report type. Here, the word METAR represents a routine report. If SPECI is in this location, it indicates a special, non-routine METAR weather report, which means the report was issued at other than the regular time, and there has been a significant change in the weather since the last report. The next element contains the station identifier. Notice the METAR code uses the ICAO, International Civil Aviation Organization, 4-letter station identifier. The stations within the contiguous 48 states are prefixed with a K. Here, KDEN is the identifier for Denver. Following the station identifier are the date and time in Zulu of the weather observation. When a report is generated by an automated weather observation station that has no human intervention, the word auto will follow the date-time group. If a correction is made to a report, the abbreviation COR is substituted for the word auto. The remainder of the printout is dedicated to weather, beginning with wind. Surface wind readings make up this section. The wind direction is given first, followed by the wind speed in knots. Here, the wind is blowing from 330 degrees at 18 knots. Variations of wind speed are shown as gusts and are indicated with a G. In this example, the wind is from 290 degrees at 30 knots, gusting to 45 knots. If the wind direction is variable and the velocity is 6 knots or less, it is noted by the prefix VRB. Here, the wind is variable at 4 knots. When the wind direction varies by 60 degrees or more, a variable group consisting of the extremes in wind direction, separated by a V, will follow the prevailing wind group. In this example, the wind direction has varied from 290 to 360 degrees. A calm wind condition is indicated by 5 zeros followed by KT. The next element of the METAR report gives the visibility in statute miles. At Denver, the visibility is 1/2 statute mile. When runway visual range is reported, it is preceded by an R. The next 2 digits are the runway number, followed by the visual range measured in feet. Here, the RVR for runway 31 is 2,600 feet. The next section of the METAR report is the present weather at the time of the observation. The type of precipitation or the obscuring phenomena is shown in code and may be preceded by an intensity symbol, a proximity code, and a descriptor code. Intensity levels are shown as either a plus or minus symbol and only apply to the first type of precipitation reported. This example indicates that light rain is falling. The plus symbol denotes heavy rain, and no symbol indicates moderate intensity. When the reported meteorological conditions are between 5 and 10 statute miles of the usual point of observation, the code VC is used, indicating the reported weather is in the vicinity of the airport. 2-letter descriptors are used to provide even more information about precipitation and obscuring phenomena. Here, FG indicates that fog is the predominant obscuring phenomena. Other common descriptors are TS for thunderstorms, SH for showers, FZ for freezing, DR for low drifting, MI for shallow, and BC for patches. The common letters used to indicate precipitation and obstructions to visibility include RA for rain, DZ for drizzle, GR for hail, FU for smoke, and HZ for haze. Additional codes are listed in your manual. The next block is used to report sky conditions. The amount of coverage is reported in eighths of sky cover, and is represented by different contractions. If the sky is clear, meaning there are no clouds visible to the observer, the report will contain the letters SKC. At automated stations, the abbreviation CLR is used to indicate no clouds below 12,000 feet are detected. The letters FEW in the METAR report mean up to 2/8 of the sky is covered by clouds. A scattered layer, or SCT, means that the clouds cover 3/8 through 4/8 of the sky. A heavier sky cover is referred to as broken and is indicated on the report with the letters BKN. In this case, the clouds are covering 5/8 through 7/8 of the sky. When OVC appears, the sky is reported as overcast, which means clouds completely cover the sky. When the sky is reported as broken or overcast, a ceiling is said to exist. The height of the cloud bases are reported with 3 digits measured in hundreds of feet above ground level. Here, the first layer is a scattered layer at 800 feet, with a second overcast layer at 1,000 feet. When the sky is obscured by a surface-based layer, the vertical visibility is reported. The letters VV indicate an indefinite ceiling, and the 3-digit number is the height in hundreds of feet. In this case, the vertical visibility is 400 feet. Cumulonimbus clouds or towering cumulus clouds are observed. The letters CB or TCU will follow the number representing the height of the cloud base. In this example, the observer has reported a scattered layer of towering cumulus at 1,500 feet. The next segment of the report gives the temperature and dew point in degrees Celsius. When these temperatures are below 0 degrees Celsius, they are preceded by an M. In this example, the temperature is 10 degrees Celsius and the dew point is -8 degrees Celsius. Altimeter settings are preceded by an A and reported in a 4-digit format in inches of mercury. Here, Denver's altimeter is reported as 29.901 inches of mercury. The last section of a METAR contains remarks and is identified by the contraction RMK. This section includes operationally significant weather, as well as the beginning and ending times of the specified weather phenomena. In this example, rain began at 35 minutes past the hour. At 55 minutes past the hour, the rain ended. Pilot weather reports, or PIREPs, also provide valuable information about current weather conditions and should be reviewed in a thorough weather briefing. No other observations are more timely than the ones made by a pilot. In fact, PIREPs provide the only means of directly observing cloud tops, icing, and turbulence. A PIREP is usually received and transmitted in a prescribed format. The letters UA identify the report as a routine PIREP, and UUA identifies an urgent PIREP. 2-letter codes differentiate each block within the report. For example, OV describes the location of the aircraft. TM tells you the time when the report was made. FL identifies the flight level. And TP tells you the type of aircraft flown. These first 5 blocks must be included in all PIREPs. The PIREP must contain at least one of several weather elements, also identified by 2-letter codes. These include SK for sky cover, WX for flight visibility and weather, TA for temperature, WV for wind, TB for turbulence, IC for icing, and RM for any remarks that might be included within a report. In printed form, PIREPs appear in this format. This sample PIREP from near Centennial Airport was issued as urgent. The aircraft was on the Denver 161 radial at 14 miles. The time of the report was 1939 Zulu, and the pilot was flying at 11,500 feet in a Mooney Mark 20. The pilot reported moderate to severe turbulence between 11,500 and 14,000 feet while en route from Farmington, New Mexico to Centennial Airport. Radar reports are another important source of weather information since they identify areas of precipitation at the time of the report. Each report can be divided into as many as 10 blocks of information. The first segment contains the location identifier and the time of the radar observation. This report is from Evansville and was taken at 1926 Zulu. The observation shows an area of echoes with 3/10 coverage consisting of light rain showers, which are decreasing in intensity. The next segment defines the boundaries of the area of precipitation using the azimuth and range from the reporting site. In this example, the points defining the area of echoes are 338 degrees at 90 nautical miles from Evansville, 111 degrees at 110 nautical miles, and 262 degrees at 125 nautical miles. The report continues by indicating that the area of precipitation is moving from 260 degrees at 30 knots. Finally, it shows that the maximum tops of the clouds are at 12,000 feet, located at 324 degrees at 39 miles. The predicted surface weather within a 5 statute mile radius from the center of an airport's runway complex is called a Terminal Aerodrome Forecast, or TAF. Each forecast is issued 4 times a day and is valid for a 24-hour period. The codes used in a TAF are similar to those used in a METAR. In this example of a terminal aerodrome forecast, you can find forecast wind, visibility if 6 statute miles or less, weather, and sky conditions. Let's take a look at a typical TAF. This forecast is for KDEN, Denver, Colorado. Following the 4-letter station identifier is the date and time of issuance. The first 2 digits are the date, immediately followed by the time in Zulu. This forecast was issued on the 9th of the month at 1745 Zulu. The next group indicates the valid period. In this case, the forecast is valid on the 9th of the month from 1800 Zulu through 1800 Zulu on the following day. The forecast is calling for winds from 220 degrees true at 20 knots. Visibility is expected to be 2 1/2 miles with light rain showers. The ceiling is forecast to be 2,000 feet broken. When the wind direction fluctuates, or the wind speed is 3 knots or less, it is encoded as VRB. Cumulonimbus, CB, is the only cloud type included in a terminal aerodrome forecast. When the weather is expected to change during the forecast period, the TAF will indicate the change at the end of the report. For example, at Denver, from 0100 Zulu, the sky conditions are forecast to be clear through the remainder of the forecast. When a possibility exists for a change in the wind, visibility, weather, or sky conditions, and those forecast changes are expected to last less than an hour, they are preceded by the term TEMPO, or tempo. This report predicts that between 0400 Zulu and 0800 Zulu, visibility will drop to 3 statute miles associated with thunderstorms and rain showers. An overcast layer of cumulonimbus clouds with bases at 3,000 feet is also expected. BECMG, or becoming, is used when a gradual change in conditions is expected and should not last more than 2 hours. The forecast time of the weather is listed by a 4-digit number representing the beginning and ending hours of the change and follows the becoming indicator. When there is a 30 to 49% chance for the occurrence of thunderstorms or precipitation, you will see a probability group. Thunderstorms or precipitation expected to be present more than 50% of the time will be included in the prevailing weather or a tempo. Here, there is a 40% chance of 3 statute miles visibility along with thunderstorm and rain showers between 0000 and 0400 Zulu. This report also predicts that a broken layer of cumulonimbus clouds with bases at 3,000 feet is expected during this 4-hour time period. Now let's look at the area forecast, or FA, which also provides valuable weather information. Each forecast predicts the general weather conditions over an area the size of several states. You can use it to help determine en route weather, as well as probable weather conditions at airports without terminal aerodrome forecasts. An area forecast is divided into 4 basic sections: communications and product header, precautionary statement, synopsis, and VFR clouds and weather. The Communications and Products header identifies the office issuing the forecast, the date and time of issuance, the valid times for forecast weather, and the states covered by the forecast. The precautionary statements, a standard note on each area forecast, indicate that thunderstorms imply possible severe or greater turbulence, severe icing, low-level wind shear, and IFR conditions. The statement in this example, see AirMet Sierra for IFR conditions and mountain obscurations, alerts pilots that IFR conditions and/or mountain obscurations may be occurring or forecasted to occur in a portion of the forecast area. Always check the latest AirMet for your area of flight. In addition, all heights not given in terms of mean sea level are noted in the forecast by the abbreviations AGL for above ground level or CIG for ceiling. This section of the area forecast is the synopsis, which contains a brief summary of the location and movement of fronts, pressure systems, and circulation patterns for an 18-hour period. This synopsis states that there is an upper-level trough in north-central Montana through southern Idaho that will move east into the plains by 00 Zulu with an upper-level ridge building over Washington, Oregon, and Northern California. There is also a surface high pressure over eastern Washington and northern Idaho that will build southeastward into southwest Wyoming behind the cold front. The VFR clouds and weather portion of this section is broken down by states or areas and describes the cloud conditions, weather, and/or visibility that are marginal VFR or better. In this example, Arizona is forecast to have scattered to occasionally broken clouds in the northern half of the state. The southern and far eastern portions of the state are expected to have scattered clouds with bases at 15,000 feet AGL and a chance of isolated light rain showers after 1500 Zulu. Included in the VFR clouds and weather portion is a 12-hour forecast and 6-hour categorical outlook for each state. The outlook for this area is VFR. When weather conditions warrant, the National Weather Service will issue in-flight advisories in the form of AirMets, SIGMETs, and convective SIGMETs. Although classified as in-flight advisories, these reports are also included in computer printouts. These advisories notify pilots of the possibility of hazardous flying conditions, which may not have been forecast at the time of the initial briefing. An AirMet describes areas of turbulence, icing, sustained surface winds greater than 30 knots, ceilings below 1,000 feet and/or surface visibility below 3 statute miles, and mountain obscuration of sufficient intensity or extent. There are 3 AirMet designators. Sierra always represents areas of IFR, Tango always represents areas of turbulence, and Zulu always represents areas of icing. Here, AirMet Sierra is valid for Wyoming and Colorado and indicates areas of mountain obscuration and IFR conditions. SIGMETs describe non-convective weather conditions of greater intensity than those in AirMets. SIGMETs are issued for severe or extreme turbulence or clear air turbulence, severe icing, dust or sandstorms that lower surface or in-flight visibilities to below 3 miles, or volcanic ash. Anytime weather conditions meet or exceed these criteria, or are expected to occur within 2 hours, a SIGMET will be issued. Convective SIGMETs report areas of severe thunderstorms, tornadoes, heavy precipitation, hail of 3/4 of an inch or greater, wind gusts to 50 knots or more, embedded thunderstorms, and lines of thunderstorms. However, since conditions of severe or greater turbulence, severe icing, and convective low-level wind shear are normally associated with thunderstorms, these conditions are assumed to exist and are not specified in the report. Convective SIGMET bulletins are issued at 55 minutes past the hour and are valid for 2 hours. Appended to each convective SIGMET is an outlook valid for 2 to 6 hours after the issuance time. This outlook discusses further convective development with emphasis on lines or clusters of thunderstorms and severe or embedded thunderstorms. Another element of your weather briefing is the winds and temperatures aloft forecast. This forecast helps you calculate en route speed and performance figures for your aircraft. Winds and temperatures aloft forecasts are derived from information gathered by weather balloons released at 12-hour intervals. The forecast gives the wind direction in degrees from true north, wind speed in knots, and the temperature in degrees Celsius for selected altitudes. Forecasts for specific locations are indicated by station identifiers. Each identifier is followed by code groups which show the wind direction, wind speed, and temperature at specified forecast levels. The first two digits represent wind direction in tens of degrees, with the next two digits representing the wind speed. Where appropriate, the remaining digits record the forecast temperature. In this example, the coded group forecasts a wind from 200 degrees at 6 knots. The temperature at this altitude is forecast to be 13 degrees Celsius. Due to terrain influence, wind forecast information is omitted from any level that is within 1,500 feet of the ground. Likewise, the temperature is omitted from the 3,000-foot level and any other level which is within 2,500 feet of the surface. Since temperatures are always negative above 24,000 feet, the minus sign is omitted above this level. Notices to airmen, or NOTAMs, are usually included with printed weather reports. NOTAMs alert you to recent changes in the airspace system that could affect the safety of your flight. Here, a temporary flight restriction is in effect until further notice. This restriction is due to dynamite blasting, and only authorized flights may be conducted within 500 feet over the blasting area. In this program, you have seen a brief overview of some of the major printed reports and forecasts that are available to you in preparing for any flight you take. When interpreted correctly, these reports and forecasts help you understand the weather you will encounter in flight.
In addition to the printed reports and forecasts disseminated by the National Weather Service, there are also various graphic weather products available for your use. Some of the more common graphic products are the surface analysis, weather depiction, radar summary, and low-level significant weather prognostic charts. These charts are designed to give you the general weather picture over a large geographic region in a glance. The surface analysis chart is a good source for this type of information. Here, surface pressure, frontal areas, and surface weather information have been combined into a single graphic display. Low and high pressure centers are readily identifiable by large L's and H's. Isobars, connecting points of equal pressure, are plotted around these centers. They are normally drawn at 4 millibar intervals and are labeled with the last two digits of the barometric pressure. Here, the isobar labeled 96 represents 996 millibars. Frontal boundaries are noted by solid lines. The direction and type of front can be determined by the symbols attached to the line. The front shown here has pointed barbs on one side, which identify it as a cold front. Since the barbs are on the east side of the line, the front is moving in an easterly direction. Weather briefers may color cold fronts blue to help you identify them. Half circles identify this as a warm front. Again, the direction of movement is shown by the placement of the symbols on the frontal line. In this case, it is moving to the north. For ease of identification, warm fronts may be colored red. A combination of half circles and barbs on opposite sides of the lines is used for a stationary front. The line is usually colored with alternating red and blue segments. A line depicting an occluded front has both symbols on the same side and is usually colored purple. In addition to pressure and frontal information, the surface analysis chart provides weather observations for a large number of reporting stations located throughout the country. For each